In other words, here we have analyzed the implications of taking the projection on one of those subspaces in the ladder. What happens when we project on one of the incremental subspaces? That is also an interesting question. So, for that we must first consider the Fourier transform of psi t, and that is easy to do. Psi t, as you know, is phi of 2 t minus phi of 2 t minus 1, and you can easily find its Fourier transform. Psi cap omega is therefore going to be equal to, well, when you multiply by 2 here, you would be dividing by 2 in the other domain, and of course, here you need to take care of the minus 1. So, e raised to the power minus j omega times the same expression. We can evaluate this. So, I think maybe we should, it would be better to come to this a little more systematically. So, phi 2 t would have the Fourier transform phi cap omega by 2 multiplied by half. Now, phi of t minus n would in general have the Fourier transform e raised to the power minus j omega n times phi cap omega. And when we consider phi of 2 t minus n in general, so here we are going to replace t by 2 t. We should take this replace omega by 2 and then multiply by half. So, this replacement must be in the whole thing, and therefore, phi of 2 t minus n would have the Fourier transform half e raised to the power minus j omega by 2 times n phi cap omega by 2. And therefore, we need to make a little correction here. The correction is we need to replace omega by 2 here. So, in fact, let me rewrite that part of the expression, it is more convenient. Psi t, which is phi 2 t minus phi 2 t minus 1, has the Fourier transform phi cap omega by 2 minus e raised to the power minus j omega by 2 times phi cap omega by 2. And if we aggregate terms, we have phi cap omega by 2. And this is easy to write. This is half. Well, we can play the same trick. We can extract an e raised to the power minus j omega by 4 common from here and get 2 j. I am skipping a couple of steps, sin omega by 4, and we know the expression for this. This is essentially 1 by 2 e raised to the power minus j omega by 4 times, well, I will continue on the next page. It is a little complicated, but not too difficult. Sin omega by 4 divided by omega by 4. In fact, let us multiply all this and put it together. So, I have e raised to the power minus j omega by 2 coming together, j there, sine squared omega by 4 divided by omega by 4, and a factor of 2 remains outside. So, what we need to focus on here is essentially this part. This is important. The rest of it is not, because it is this that really affects the magnitude seriously. The rest of it is essentially a constant magnitude. So, let us look at the magnitude of sine squared omega by 4 by omega by 4. First, let us look at sine omega by 4 by omega by 4. That of course, would look like this. You see, this is the point 4 pi, minus 4 pi, and so on. And then on the same graph, I will draw, so this is mod sine omega by 4 by omega by 4, and on the same graph, I will show in dotted mod sine omega by 4 once again. So, that is going to look like this. It is going to have a maximum at pi by 2, and then it is going to cease omega by 4. So, one cycle will be completed when omega by 4 equal to pi, that is omega equal to 4 pi. So, you have one cycle being completed here. Mod sine is going to look like this. So, in each span of 4 pi, you have one half cycle being completed, right. So, this is one half cycle. Now, in the next span of 4 pi, again you have one more half cycle being completed, like this. This is the situation. Now look at the situation. This was the 0 frequency here. The solid line has a maximum at 0 and it tapers off up to 4 pi on both sides. The dotted line reaches a maximum in between at 2 pi, when omega by 4 is equal to pi by 2, all right. So, omega is 2 pi. This point, the maximum here occurs at 2 pi, and therefore, when you multiply this decreasing function by an increasing function here, there is going to be some point of maximum in magnitude somewhere in between 0 and 4 pi, and it is going to taper off to 0 at 4 pi again. So, let me focus, you see in the other side lobes it is easier to understand. For example, between 4 pi and 8 pi it is very easy to understand. You are multiplying essentially two similar looking functions, and so you can see there is going to be a maximum somewhere, it is going to taper off. And it is also clear that the maxima in the other side lobes are going to be weaker than the maxima in the main lobe here. All this, so when you multiply the dotted function and the solid function, you are going to get a pattern something like this, which I now sketch. Something like this. This is going to of course be mirrored on this side, and then this way and this way and so on. So, this is mod sine squared omega by 4 by omega by 4 as a function of capital omega. Let us take a minute to look at this. When we take an inner product of a function x t, now here I am writing t to explain that the inner product is in time with say psi of t minus n. In the magnitude sense, what are we doing? We are first multiplying the Fourier transform of x t with the Fourier transform of psi t minus n. This should be understood to mean the Fourier transform of psi t minus n, a cap on the whole function. So, when you multiply them and then integrate, that part of the Fourier transform of psi t minus n, which is significant in magnitude, is going to be extracted out of the Fourier transform of the original function x. And what is that significant part? Let me put it back here for you. It is therefore going to give emphasis to a band now, not a band around 0, a band around some other frequency here. Of course, there is symmetry, there is always symmetry in frequencies. So, you could focus on the positive side of the frequency axis, but what is going to be done is to emphasize a band here. And instead of psi of t, if you take psi of 2 t for example, so if you take, say, instead of w 0, if you go to instead of w 0, go to w 1, in which case you would have psi of 2 t minus n. And how would the Fourier transform of psi of 2 t minus n look? So, if you take the magnitude, if you take the Fourier transform of psi of 2 t minus n and plot its magnitude, its appearance would be something like this, it would be stretched. So, instead of going from 0 to 4 pi now, you would have a band between 0 and 8 pi. Of course, symmetrically on the negative side. Now, there are two things. You see, you must keep in mind that unlike the case of phi, in psi we have two changes taking place. One is that the band expands, the main lobe expands and each of the side lobes expand. But the second is that the center frequency, the point where this was a maximum here, you see this center frequency also doubles. Both the band and the center frequency double. So, that means now you are emphasizing a different band. The center frequency is different. Each time you go to a different W, you take W 0, you are emphasizing one band. When you take W 1, you are doubling the center frequency. So, you are emphasizing a different band, and of course, the band itself has doubled also. When you take W 2, you are again doubling the center frequency. So, you are emphasizing a different band and again the band is doubled. So, each time you are doubling the band and you are doubling the center frequency. So, in a certain sense, that idea of complementarity, each time you put one incremental layer, you are putting one more band and the band size is doubled here. Now, where in all this is our discontent with the Haar? Why are we discontent? The discontent is because even if we say we are emphasizing a band, it is only true to a certain extent. Let me put back this Fourier transform and illustrate. We might say to an approximation that we are emphasizing this band, but that is only approximate. We are also to some extent keeping this band and this, and there of course, the negative corresponding pieces, and that is where we are not content with the Haar. We want to keep a certain band, focus our attention on it. We do not want interferences from the other side lobes that are there. And in going to other multi-resolution analysis, we are essentially trying to reduce that unwanted presence of the side lobes as much as we can. We have given a feel of what our discontent is like. We shall build on this further in subsequent lectures. Thank you.